One of these days I'm going to get really fancy, like mount a camera on this.
Oh yeah, that'd be sick.
All right. So when we're looking at an equilibrium system, okay, it tells us here that we have a mixture of hydrogen and nitrogen in a reaction vessel, and it's allowed to attain equilibrium at 472 degrees Celsius. Okay, the equilibrium mixture of gases was analyzed. First thing, and I want you to highlight this. They're telling us what the values are at equilibrium. That's going to be important here. Okay, there's all of our numbers. Okay, from this data, we want to calculate our KEQ. Now, KEQ is like the general term for KC or KP. Right? It's like not telling you specifically, it just means a K. In our case, which one would I want to write, a KP or KC? Yeah, we're going to have to do a KP because we're given pressure values, not molarity values. So let's start by writing that. Right, when I'm problem solving, I always start with, well, what is the goal? The goal is KP. The setup for the equilibrium expression is always, I'm going to switch colors here, products. So we're going to have the pressure of NH3. So hopefully this is ringing a bell. This is what we did on our homework last time. To the power of 2 over the reactants. So we're going to have the pressure of H2 to the power of 3, and then the pressure of N2. So what I've done so far is what we learned last time of setting up an equilibrium expression. Questions so far? Okay. Now, just to remind us what this is, what does it mean? Can someone define for us by raising hand? What does it mean when a system has reached equilibrium? What does that mean? Yeah, go ahead, Allie.
Just like that it's still it has the same ratio, even though I don't know how to say it other than reaction, so it's happening with the ratio.
That was beautifully said, right? It's all about, it's reached a magic ratio. We don't know what it is because we're solving, but it's reached this ratio of products to reactants, and at that point, it can still be changing, but every time a student goes out, another student comes in, and so the ratio is maintained. Okay? So, since they are giving us the values at equilibrium, we just plug them in. Allie, have a smiley face for that, by the way, if I didn't say that. Okay, so NH3 is 0.166. Now, don't lose the powers when you start plugging things in. That's a common thing sometimes students just forget. So keep that squared over the H2, which is that 7.38. And that has to be cubed, and then 2.46. Right? Maybe if you want to draw arrows to remind yourself where these numbers are coming from. The best thing with your notes is you want your notes to tell you a story of how you got to the end. Right? Because otherwise you just look at it and you're like, how did I get from here to here? And then just let your calculator do the work. If you plug it in correctly, I got 2.79 times 10 to the negative 5th. That's my answer. Yeah, Emily.
So what does that number represent? Is that the time it takes?
Oh my gosh, you stole a question out of my mouth. I was about to ask you guys that if you didn't ask it.
Why do they give us temperature?
Oh, great question. So I'm going to come back to yours in a second, Emily. So what Aguilar asked was, why did they give us temperature? The significance of the temperature is just the fact that it can't change. Whatever this value is only true at this temperature. So it's true for this reaction at this temperature. But if the temperature was 500, we couldn't say this is K anymore. Does that make sense? So that's why they'll always give you a temperature, but we never will actually use it mathematically. Great question. I'm smiley for that. So with that number, so we mentioned last time, and are there any units attached to this number? No, makes your job easy. There's no units ever. because of what it represents. It represents a ratio. So I want you to write it slightly different, but just for understanding's sake. This is what you would write as your answer. But for understanding, write it this way, because I think it will help you understand what it means. What this means is there are 2.79 times 10 to the negative fifth products for every one reactant. So the number you get is a ratio of products to one reactant. So don't say anything out loud. I'm going to have you point in a second based off what you think. Okay? Do you think there are, so does this mean when I achieve equilibrium, are there more products in my reaction or more reactants? Point accordingly. So products point to the window, reactants point to the wall. Which one do I have more of? This will help me understand your understanding of the ratio. Alright, so the correct answer is we have more reactants. Because, and maybe some of you, this is 10 to the negative 5. So this is a very small number in comparison to 1. So what we would say, and we'll use this term as we go, we actually would call this a reactant favored equilibrium. And that's a common phrase like you'll see in questions, is reactant favored or product favored.
Would it just say like, is it reactant?
Yeah, like sometimes I've seen questions where like, is this a reactant or product favored equilibrium? Yeah, Alex.
And you would always compare that to one reactant?
Yes, because that's the whole idea of once we divide them here, the bottom of the ratio is always out of 1. So yeah, good question though. Any other questions before I have you try a problem with your buddy? Okay, go ahead and try this practice problem for a smiley face with your table buddy, and then we'll check it. Ready, set, go. I'm gonna go fill my water. I'll be right back.
So, pressure, and then
So, put the stuff in the stuff. You know what I mean? Put the stuff in the stuff. Well, no, so you're gonna set it up. Bryson, you already did this. Wait.
I was just round.
Two known values and a known value. Yeah, it's a known value.
I thought it was just like. I don't know, or just, 13.
You guys got that right.
We're also doing stuff. Give me a question and then you do a question. Yellow. Why? Why do you why? Let's try. It's a word. Pretty sure. I mean, I just said it. It has vocabulary. Vocabulary. You are going to leave the rest of your stuff. Sure. Stop.
No,
No, it doesn't. It shows you're going insane.
I don't know, I'm always.
I don't want to say this. Oh, I'm bored. No, you don't have to. Oh my gosh. Stop.
Yeah, we're gonna look
Stop.
Okay, sorry guys, the water fountain way too far away.
It's so far away.
No, you do it yourself. We're scaring the corner.
How darest thou?
Maybe you need to go even like press even harder. You're doing this to yourself, man.
Yes. 110. Okay, anyone need another minute? Are we ready to check it?
Give us like 20 seconds.
Did you guys all get 110?
Oh, what?
Or 109?
Oh, I knew it. You had to do the squares. I originally did the squares.
Oh, we did the script.
I know, but it's like.
Ah.
Yeah.
Hey.
The two? Yeah. In a sense, it's incorrect.
No, I'm just doing the opposite.
But it's square.
Ifra.
So it is square.
Because don't cut it.
But
You just shouldn't be at a table.
you just said 109?
I should have said that if I ran to go my water.
What? Then why did you say 109?
The square always comes from
Yeah, she did say 110. No, she said 109. She said 110 at the beginning.
Subscripts and then I very
No, because class has only 110 only has 2 students.
What? That
Okay, I think I walked and checked everybody. If you got 110 rounded for sig figs, you can have a smiley face because you're correct. Any questions so far before we do another problem? Okay, focus back up front, up with me everybody, because things are changing. As fun as those problems were, they won't all be hard. Okay? Alright, so this problem here, what I want you to notice is once again the difference. Because the goal is actually still the same, but our approach is going to be different based off what is given. And that is key because otherwise you will try to do what we just did again and it won't work out for you. Or vice versa, you might try to do this in a problem you don't need to do this, and you can just plug the values in. Okay? So it says here that we have 4 moles of each X and Y are placed in a 1 liter vessel and allowed to react at a constant temperature according to the equation above. 6 moles of Z is produced. What is the value for the equilibrium constant Kc? So, same initial thought, so let's write our Kc expression, just to have that in mind. So Kc is always products over reactants. So it's Z squared, once again we're using molarity now because of what they're giving us, over X and Y. Now, can anyone recognize why I can't just plug 4, 4, and 6 into this problem? Can you tell me why it won't work this time? Brian, what do you notice?
It's not the molarity, it's the amount of moles.
Perfect, so there's one problem. This is a mole. Brackets stand for molarity, and so you can't plug moles straight in. So that is one problem. So good catch, Brian. Have a smiley face for that. How do I change moles into molarity? What did I just say? Did I say that right?
Yeah.
Okay. Yeah, how do I get moles into molarity? Moles per liter, so it'd be 4 divided by 1, which is still 4, 4, and 6. But those I still can't actually use. But it is something to consider because that is a key part, especially if it's not a 1 liter vessel. Anyone else notice a problem with my numbers? Kenzie?
So it wouldn't be balanced? Or would it?
What do you mean by balanced?
Well, so there's 4 moles of both X and Y, and those have to be the same, but that has to be double. Z will be double.
Oh. I'm glad you see this. It's not correct, but I'm glad you pointed out because I think it's a common misconception. Have a smiley face for this. So the ratio at equilibrium doesn't have to match the ratio of the balance equation because it's just whatever its equilibrium balance needs to be. They're always going to change, like it's always going to react one of these to one of these to make 2 of those, but it depends on how much you started with and then what the final end balance needs to be. But thanks for pointing that out, Kenzie. Jack, do you have another idea?
No, I don't think it's right.
That's okay, you can still get a smiley face.
Mine was wrong.
No, but have a smiley face, thanks for trying. Anyone else have a thought? Zach?
It's because there's no temperature?
No, but that is an interesting observation that they didn't give us that. Have a smiley face for that observation. There's something else about it. It goes along with what we highlighted in the last question. That this question is different.
Oh, it's not
It's not at equilibrium. One value is, which value is at equilibrium? The 6. What are the 4 moles at? The beginning, those are like the initial amounts. So when the values you have are not at equilibrium, because K means equilibrium values, the ratio at equilibrium. So if the values given are not at equilibrium, you need to think rice.
Ooh, I love
What's the marker?
We're eating rice.
Yep,
I want rice.
that.
rice.
Run inside.
I like yours.
I'll tell you.
All right, rice is a problem-solving method to help us understand where we started and where it's going to end. Okay? This is not something I made up, by the way, so don't give me credit for it or hate me for it.
I will
Either way.
give you all the credit.
Okay? I guess true. If you like it, give me the credit. If you hate it, it wasn't me. Okay? So R stands for the reaction, so we want to look at the reaction. Okay? So I'm going to just rewrite, so whenever I write R, I just rewrite the reaction next to R because we want it in our table. Because the columns are going to play a key role here. So I'm going to write X plus Y, equilibrium arrow to Z.
You forgot the stages.
It doesn't matter in this case. Okay, I stands for initial. So what did the reaction start with? C stands for the change it's going to undergo. and E, you can kind of think of it in two ways. For this unit, we're going to focus on it as it's the equilibrium. But you could also just think of it as the end. Like, what is it going to be when it reacts to the end? All right, I'm now going to use different colors to show you the order at which you should fill in any rice chart. So if you want to match with me, you don't have to match the color, but if you want to use colors to coordinate. So step number one, once you have your rice chart built, is to put in what is given. So I'm going to do these in red. Okay, so we're going to write in everything that the problem gives me. Now, side note here with rice charts, you can only put moles and pressure into a rice chart. You can't put molarity in because molarity is not additive, and no other unit would work. So only moles and pressure work for rice charts. So that's why I'm not going to convert them to molarities yet. Okay, now that we have our side note there, so what is given in my problem that we can plug in here?
4 moles of X and
Perfect. Initially, I'm starting with, in red, 4 of these and 4 of those. Thanks, Alex. I missed my piece of that. Right, so the problem told me, all right, we're starting with 4 moles of X, 4 moles of Y. What else is given in the problem? Where would that go, Bryson?
Where the Z is. Underneath the Z.
Is that how much I'm starting with or ending with though?
Oh, and then that's
Good
at the
catch.
bottom.
So Bryson, notice, so it says we have 6 moles of Z being produced, so I'm going to put that down there. Because it's being produced, so it's the end amount. Okay? All right, there's one more, I guess you could say, read between the lines given, and that is, if initially I only start with this, so since they told me this is going to be 0 because they haven't reacted yet. And if they haven't reacted yet, you're not going to have any Z in the beaker. Right? So when they tell me I have like 4 and 4, right, they're saying there's no Z left. So this will often be 0 because it hasn't reacted. The only time it wouldn't be 0 is the problem would tell you a number. So that's what I mean, like read between the lines idea. Okay. Nothing else is given, so I'm going to switch colors now. Okay. Step number 2. Pick a new color here. We'll go green. Okay. Is determine. Oh, this screen is struggling. Oh, that's not going to be big. All right, we're going to determine the change from the given. Okay, so we're going to determine how it changed because of what was given. So, if I had 0 Z in my beaker, and I ended with 6 moles of Z, then the change for Z must have been +6. Adding or plus or minus is very important on the change rule because it helps you identify, is it reacting and being made or is it being used up? So plus sign means being made, minus means being used up. Okay? All right, questions how I got this number? All right, change color again, step 3.
Oh, wow.
Once you know one of the changes, you can determine the rest because it will match the ratio in the balanced equation. So we're going to determine the rest of the changes by matching the balanced equation ratio. So the change and the reaction will always have the same ratio. Okay, so like these two, you can kind of like ratio should be the same. So, since it's a 1:1:2 ratio, if this is a 6, then this should be a 3. And in this case, the sign flips because we've crossed the arrow. And these things are being used up now. But the number, and then what would this one be? Good, also -3. Now, I didn't realize this till last period and it was too late to go back. It's kind of a bad first example because it may give you the wrong impression. It gives you the wrong impression. This does not have to equal this.
Oh.
It happened to in this case. But moles are not additive in that way. Remember, 2 moles, 1 mole plus 1 mole can equal 1 mole. Because if X and Y became XY, it's 1 molecule. So from here on out, every problem we do after this, it's not going to match. So I realized it was a bad first example because I don't want to go away from it again. So do whatever you need to recognize for yourself. Like, don't connect that, right? The connection here is 1:1:2. 1:1:2. That's the connection that will always be true. Okay, good so far? All right, 4th color, final step. Hopefully you can see where it's headed. Final step is determine the equilibrium values. So I'm going to have 1 mole of X at equilibrium and 1 mole of Y. Then once you finish your beautiful rice chart, now we can take these numbers and plug them in here. So I'm going to have 6 squared over 1 times 1. So my equilibrium constant will equal 36. Yeah, Lily.
So, would you ever, like, if our leaders weren't one, would you ever turn it into molarity instead?
Thank you. Yes, I did turn it into molarity. I just skipped ahead because it was 1 liter. But that is such an important thing to recognize. Lily had 2 smiley faces for that reminder. If the volume wasn't 1, you would first have to divide each of these by the volume because brackets mean molarity. So I did, if you want to maybe put that on there to remind you, like, we're going to divide this by 1 liter. Because if it wasn't 1, then obviously that would change your numbers. Lily just saved all of you. Okay, any questions before I have you try one with your tables? Yeah, Zach.
What's the, like, throw everything to the K formula? What's the use of Q formula?
Stay tuned till next Tuesday, and we'll talk more about Q. But we will bring that back up. But yeah, great question. Okay, I'll give you 4 minutes. Try this one as a table. When you have an answer, raise your hand, and I'll come check you. But your whole table needs to be in agreement before I check you off. Okay?
Charge.
Are we doing B or C?
B. Yeah, start with B. C has a little twist. If it helps, anytime it says example, I'm going to do it with you. When it says practice, you'll. Not if anyone but me notices that, but that's how I set up the notes.
Yeah.
Oh, I made it feel hard.
Well, we just learned this.
That's just Kelvin, like that. I'm using that K.
Because it's 0.
Then if there's potassium in the
Oh, yeah, it's
solution,
just
oh, right. What are we doing? It's Kelvin.
I don't think so. But it also doesn't give us. Yeah, it doesn't give us given values for it. Okay, so Ooh, that's interesting.
Yeah. It gave us no initial value for
Really? So you are united.
but I don't think it's 0 actually, the initial value, right? And we can still figure it out from the check.
Pause there. We already used that. The initial amount should always be something they have to tell you. They do tell you. Where?
2, so
So they tell you that with SO3 at a partial pressure of. So start, make your right choice.
2, 2.
Let's write out right. So it's a good place to start.
Yeah. It's diagonal.
Oh, are given?
Okay. So what initially?
Pressure.
So they tell us initially we have 0.5 of SO3. So that would be your initial amount there. And then what's the one other piece of data they give us? Where are we at? That's at the end. That's the end amount of.
I don't know something I'm doing. It's gonna plug them in and then.
Again, I know it's like it is for S.
Wait, so where would the 0.2 go?
Oh, you're saying for 0.2.
But where would we put it?
It's all in there.
Oh, it'd be a SO3.
Okay, so now there's one other initial you can always read between the lines.
That doesn't.
You know what that is? The initial of the products is gonna be 0, because they have them. So put 0, 0 under the SO2 and the O2.
Wait, first.
Now, if you know it started with 0.5 and ended with 0.2, what was the change? So you know, went down by 0.3. And as soon as you know one change, now you bounce the ratio.
Yeah.
Oh, positive, but match with this. You want a 2 to 1 ratio.
So we don't take it.
This is 0.3.
Oh, because never mind. Well, I feel like that's a hat. I feel like that's a square. So negative positive.
It's gonna be,
This is 2 to 2. 0.3 of that.
this one's gonna be twice.
But that doesn't make any sense. What is negative pressure?
So it would be negative.
And the last one would be 2 to 1 ratio. Okay, we look like we can use some more time, which is fine. I just picked a random number. Continue working when you're ready or need help. Let me know. Are you guys good to keep rolling? Yeah.
But the SO3,
And then this is.
So the balanced equation does not include the initial. Again, you can initially start with whatever you get. That one increases. That's about
O2 is still.
That is the whole video I wrote.
Yeah, because they said it would.
I got 0.2.
Call me back if you need that.
Products are also going by zero.
What did you get price?
This is twice. It's 2, 2, 1. So these two should be double.
Yeah, that looks great so far. Okay. So once you know one change,
How do you know that it's double?
you can always find everything else, you just have to follow that ratio.
Why would you not?
Spoke up. Or you were just finishing it up. He was
Oh, did you remember the X one?
The O2 is
Good answer.
and if you have negative O2, since there's a square, it would be a negative since the O2 is it doesn't count, then it comes out to be a positive. But I don't know. It feels weird. Still feels funny.
Okay, what do we got going on?
Since,
Okay, let's
it's squared.
what do we know?
Why did you not square the point two? Why did you not square the point two?
I think we just now.
What do you know about?
Okay, I just put that.
Oh, wait, you want 5 for O2?
This changed by O3. This one had to change by.
I don't know if that's right, but
So that is.
so we should make 18. Wait, no, that's right.
I always put them off, and so I did it like the Saturday before the Monday of the retake, and I bombed like 3 of them. It was so bad.
So what did you use for your one? Obviously, I'm not like,
I just kind of.
That should be the 630.
extra credit that one. I think I only 1.5.
That's true, because I think people have to think of
Okay, I was like,
Be included in your rice, but you're never gonna plug the O2 back into the equation because remember when we did the equation, we never included the O2 in the equation. We wrote out because it's diagonal. So like, yeah. Back for example, the first example is 7.3a. Wait. Where was it? Oh, was it because? Where did we do that?
I do think that.
Okay.
If you put in money for
I just don't know what it is for. Oh, was it the?
put in $10,000, you have to answer. Because a stock is like
It would.
and now it's like $297.
No, I couldn't because I wasn't alive. Okay, I think I checked all the tables. Nice. Okay, questions about this before we do another exercise together of similar, but let's change things slightly?
You didn't check how to do this. Yeah.
Did I miss your table?
Yeah.
I was walking around. Did you get 0.338? Oh, you didn't?
I just routed it. I think I did something wrong with that.
Oh, you just need to. This is right. Just type it in again. Oh, no negative. There shouldn't be negative. That's gonna change. I don't know that. I mean, it wouldn't, but because this. So when you cross
Oh, you
the arrow, the sign flips because if these are being
That makes
used,
sense.
then those are being gained.
That makes more sense.
So, but other than that, your setup's look great. So I just try typing it in again. Okay, what I want to do before we try another one with a slight twist, because that was a lot to take in at once. So I'd like you to everybody stand up. Stand up for me. Take a stretch. All right, with your table buddy, what I'd like you to do is figure out between the two of you whose birthday comes next chronologically.
Mine's next week. What's yours?
Moving forward.
Mine's at the end of the year.
Did you just
Unless mine's like.
Did you ever figure it
Yeah,
out?
when's your birthday?
Okay, so then what you're gonna do, if you are the chosen one, meaning your birthday comes next, you're gonna take a quick 90 seconds and re-walk them through how you solved this problem. Just the one, yeah, the one you just did. Ready, set,
Why? Because this has to go somewhere. It's going to. So then we plug the value next
Thank you, Porter. You're welcome.
Alright, have a seat when you're done teaching. You're much faster teachers than me.
Yeah.
Okay. Any follow-up questions people have? Remember, questions give me warm fuzzies, so don't ever be afraid to ask. Okay? Alright, let's look at the next one. Same goal, but there's something a little different we have to approach it with. Okay? Alright, so the question says here, okay, that we have a pure sample of PCl5 is placed in a container. The initial pressure is 1 atm. The temperature is held constant until it reaches equilibrium with its decomposition products. The total pressure at equilibrium is 1.4. What is the value for Kp? So to start off, I'm going to write my expression because I know I'm finding Kp. That way I keep the end goal in mind. Alright, so Kp is always products over reactants. So we're going to have the pressure of, we have a lot of P's in here, PCl3 times the pressure of Cl2 over the pressure of PCl5. Right? Always good just to start with your expression so you know where you're going. You don't forget when you plug it in at the end that you don't forget to do products over reactants or vice versa. Okay? Now, don't say anything out loud, but on the count of 3, I want you to give me a thumbs up if you think a rice chart is going to be needed, or a thumbs down if not. Okay, so I'll give you a second to look at the board. Thumbs up, yes rice chart. Thumbs down, no rice chart. Ready? 3, 2, 1. We do need a rice chart. Can someone expound for us why? Yeah, Bryson.
Is it because we know the initial pressure of PCl5 that is 1, but then the total pressure of equilibrium is 1.4, so then we have to calculate for that change?
Yes, right? It's like the keywords of we're not at equilibrium. So that 1 can't be plugged in. We have information at equilibrium, but we don't have enough. Okay, so that's how you know you need a rice chart is because you're not at equilibrium yet. Okay, if it just gives you equilibrium values, you can just plug them straight in, like we did on the first 2 problems. Okay, all right, so let's set up our rice chart here. I'm going to use my same color code as I did before, so if you want to do the same. You know what I decided? Sometimes you guys don't like enjoy rice charts, but it'd make it more fun if every time we did one, we like threw rice in the air.
Yeah. Did you get revolved already? That sounds like a great idea. You have like a standing floor.
It'd be like slippery. But I just want you to like be excited about a rice chart. Not like, oh, I have no rice. Okay, anyways, I don't have any rice for us to throw today. All right, red marker, initial. What do I know initially that I can plug into here? Where do I put it, Marissa?
At the initial for PCL5.
Good, so I know that this is 1. And then we can do the in between the line ones that says they didn't tell us anything, those must be 0. Ian Marissa have smileys for that. What else is told initially? Eva?
You know that the pressure at equilibrium, for PCL5 is 1.4.
Close.
Wait.
Read it one more
Oh
time.
wait, never mind. Opposite. The other big star.
Nope, read it one more time.
Never mind.
No, what is that 1.4? Just read it.
Total pressure. Oh, everything.
Yeah, so this one doesn't give us any of our E's directly. What does that 1.4 have to do with it?
All the
These are going to equal
See if it don't.
1.4. Everyone see the difference there? Because it's a total pressure. Yeah.
So we have in change plus 1.
Not quite, but you're on the right track. So looking right here, everybody, is a little bit different because last time we had an initial here and then we could like, oh, what's the between? Go from there. We don't have anything here besides the fact that we know they're going to add up to this. Now we can't assume the ratio is equal and it's just going to be 1 to 1 to 1 and divide this by 3. But it's not, because that would be assuming the equilibrium ratio is that way. But you are on the right track that we can use the 1 to 1 to 1, then change. Keep in mind, this is the only one where the ratio applies. This isn't 1 to 1 to 1. This won't be 1 to 1 to 1. I mean, it could be, but that's like 1 in a zillion chances. But the change will always match this. Any thoughts of what I could do? Zach?
algebra.
Algebra. I don't know what it is. But I know this has to go down by something, because these have to be made, right? Like if I'm gonna get to equilibrium, I have to make this. I don't know by how much, so let's call it X. Zach?
Because we know it goes up 0.4, and we know that the reactants that would have double the pressure that the initial one does, can't we just subtract 0.4? Because it would, you take 0.4 away from the first one, and then the other two would add 0.8, which would give us 1.4.
You're just filling in my rice chart without writing it back, but yes, that is what we're gonna get. So if you don't know, so the time you have to use X's is when they don't give you anything here. Now, just to clarify, because once again, I should have given maybe a different example. If there was a 2 here, how would that change my X's? That would have to be 2X, right? Because it has to match the ratio, right? This has to ratio to have to match. Okay, so now I'm going to carry them down just like before. I'm going to switch to brown. I don't know, was that blue last time? I lost track of my colors, but okay, 1 minus X, X, and X. So I just carried down the initial to the change. Now, in a sense, this is my answer, right? Like I'm going to put in 1 minus X here, X and X there, but obviously that doesn't give me a number. So knowing that they add up to 1.4, I can solve for X. So there's a variety of ways you could solve this, but the best way when you're solving is to combine like terms. So you have a negative X plus an X, which would go away, plus an X. So this can simplify to 1 plus X equals 1.4, because in a sense we just combine those away. Then get X by itself minus 1. So X equals 0.4. Huh?
I feel that.
Everyone okay? So then, what gets plugged in here? Yeah, put x back in to find their values. So this is just 0.4, so I can put 0.4 times 0.4, because it's x and x. And then the bottom should be 1 minus x. So 0.6. Question, Garrett?
How do you mix minus x to the BCL5?
Great question. So the catch is, I know that some of this has to go away, right? Because we need to make these for it to be at equilibrium. So you always just pick x, but just based on the balanced equation. So in our case, since it's 1 to 1 to 1, it's just x, x, x. But if it was like, if there's a 2 here, then I would say minus 2x. And then plus x and plus x. But just always say, well, I know some of this has to be made, so let's just say some amount, let's call it x, and then match the ratio. Does that clarify that? Good question. Any other questions? I don't even know, what was the answer we got? I didn't even write it down. 0.27? Sounds good. Questions on that one? So, when do I have to use a Rice chart? When it's not at equilibrium. When do I have to use x's? When I don't have any equilibrium value to start with. Okay? But caution, don't go x crazy now. Because sometimes students learn this and then they try to solve problems like this one and start throwing x's into the problem. That just makes it real messy. So, okay. Any other questions before we just wrap it up with our last topic? Okay, flip it over and let's, so really the last objective is really understanding what this number tells us. So that's what 7.5 is. So your homework 7.4 is all about finding K's, whether it's setting up a Rice chart or not. And then you have some AP classroom quizzes. The first two are about like conceptually understanding equilibrium. And then 7.5 is understanding what this number tells you, right, the value of it. So let me get rid of this here. And I'll help you fill in the blanks that I just didn't put on this slide. The first one is the value, okay, that the value of the constant provides us with important information about the composition of the mixture. Okay, so if we're looking at this reaction here, you can fill this blank in. What would be the Kc expression? So plug in products over reactants, so put COCl2 on top, CO and Cl on the bottom. Someone did the experiment and they found it has an equilibrium constant of 4.56 times 10 to the 9th. Okay, which means, once again, that means adding, moving the decimal over 9 places. Okay? So, in order for this equilibrium constant to be so large, right, this is a really, really big number, that must mean that you can write it two ways. If you want the fancy math term, write numerator. If you want the non-fancy math term, write top of the fraction. That's what a numerator is. Okay, that the top of the fraction of the equilibrium constant must be much larger than the denominator or the bottom, right? In order for it to be really big, the top number must be a lot bigger than the bottom number. What this is telling me, once again, is there are that many products for how many reactants? 1. Right? You have this many products for every 1 reactant in your ratio. Okay? So in general, as we mentioned at the beginning, the terms we use is that if K is greater than 1, once again, keep in mind that K is always products over reactants. So if K is bigger than 1, which one of these do I have more of? Products, right? So this is what we call a product-favored equilibrium. And then vice versa, if it's much less than 1, we call it a reactant favored. Don't say it out loud, but think in your head, and then I'll have you discuss with your table. What would it it mean if K equals 1? Don't say it out loud, but think for a second. Share with your table what you think. Ready, go. What would it mean if K equals 1?
One to one. Thanks, Einstein. Stephen Hawking. Or is it always gonna be like 0.0001?
In science, I never like to say like never or always.
Science is everything.
Because, yeah. But I've never seen one that equals 1. So, but there's some that can be close to it, but I've never seen one that actually equals 1 on the dot. Yeah, Garrett?
Like, if it's like 1.5, is that fairly close?
Yeah, I mean, technically you'd still say it is product favored, but not like heavily product favored, right? Because that one means, oh, you just have barely more than the other. So yeah, anything past 1, technically you can still use the terms, but compared to like these ones where it's like extremely product favored. So yeah, good question. Okay, let's look at one last practice problem here. Visualizing like what this number is telling us, okay? All right, so this one says an equilibrium constant for their given reaction varies with temperature, as they all do, okay? It follows this. They said that the K is 794 when I'm at 298 Kelvin. I know this is confusing because there's K for Kelvin, K for equilibrium, a lot of K's right now. What I do, when a problem straight up gives me the K, as I'm reading the problem, I label it really quickly. What is that number telling me? So what is it telling me if its K value is 794? I label my K if it's given straight away, because it's probably going to come into play somehow. All right, then it tells me the K changes, because it changes the temperature. The K is now 54 at 700. So what does it mean if the K is 54? Is it product or reactant favored? Product. I'm going to label, because we know there's a comparison here, that it's less product favored. But still on the product side. Once again, if you can kind of interpret the numbers as you read them, the question becomes pretty clear. All right, the question is this. Is the formation of HI, so the next thing is what are we focused on? Is HI a reactant or a product? A product. Okay, so is the formation of product favored more at higher or lower temperatures? Well, if I compare the two scenarios, the lower temperature gave me more product. Everyone see that? This one is a lower temperature. Yeah. So the answer is simply that is it's favored at lower temperatures. So this is kind of what I mean by understanding what that value tells you. Questions on that? Okay, the next problem, I decided last period I don't like it yet. So we're not going to do it today. Because it will make more sense next time. So I don't want to confuse us, because I feel like we're at a good place right now with where we're at. Okay? So 2 homework assignments. You have your worksheet 7.4, which is practicing calculating Ks, and then AP classroom quizzes 7.1, 7.2, and 7.5, where 7.5 is about this idea of what it represents. 7.1 and 7.2 are kind of looking at equilibrium graphs, like those plateau ones we looked at last time. So, any final questions? We got 3 minutes. What do you want to ask?
Let go home.
I know, I'm sorry. If I was a college professor, I could just let them leave. They could do that. They can just cancel class whenever they want.
That's my favorite part.
But I can't.
Probably English. Probably gonna say something in English. And you know,
I don't remember what you did.
it's still a homework.
So are you gonna do so long?
I mean, maybe. I don't know. I mean, it's highly recommended.
I just thought Summer said you would give him $1 billion.
Never been done. Have to be private. Please, I don't want to do it.
The only reason to meet you got out.
Oh, that's awesome.
Yeah. Got his car.
I was so
I would just see it.
right, yeah.
And Molly did have a good point that it's like, plastics.
Oh, I would just gotcha. So my only thing to think of is, so when you're finding delta H, so you're sounding correct in that, then you gotta find the moles, the molarity, and then you've gotta use your Q to answer the 4. The one thing is, did you, and I think you were saying this, did you divide your moles by the balanced equation number? Because that's what I think the balanced equation is like there's 4. So whenever you get the moles, you have to divide it by that ratio in the end. And then that's your mole balance.
It's like you should have been slacking.
To help, if it helps you better than the song in
You should have been that little kid just hanging out in the snow for like 6 hours.
that I gave you that has like the
Every
correction
single
sheet.
day.
There's an answer key
I've
with
seen
work
them out
behind
Oh,
those
yeah,
pages.
yeah.
So if you look at that, maybe you can kind of see too of like what you were missing. But it sounds like for the most part you were on the right track. And I do remember that when I graded yours, that yours was really close.
Okay, good, thank you.
Yep.